There are 21 participants already. I just want to say hello, good morning, good afternoon, good evening, depending on what time zone you are from. We have people from different time zones. So today's webinar, again, it's one of those webinars which ANAHEI and M3 Center for Hospitality and Technology and Innovation is arranging for different type of methodologies or different topics. Today's topic is Introduction to Network Science and Complex Systems. The speaker we have today is Jalayer Khalilzadeh. His nickname is Jolly, but we'll talk about Jolly a little bit later down the road in a couple of minutes. My name is Dr. Faizan Ali. I'm an assistant professor at College of Hospitality and Tourism Leadership, which is in USF SM or University of South Florida, Sarasota, Manatee. And I also act as Director of Research Methods and Statistics for ANAHEI. I will sort of be a moderator for the session, not really that I want to moderate, but just to make sure that everything goes in its correct form or whatever we intend to do. All right, so Jalayer, I will take a little bit of your introduction from my end. Later, if you want, you can talk more about yourself. Jalayer is a PhD candidate at Rosen College of Hospitality Management at University of Central Florida. He has worked a lot in the hospitality industry, and he really has a lot of interest in neuroeconomics, network analysis, game theory, etc. So I recently met him, well, I know him for quite some time, but I recently met him at the graduate conference, and then we talked about some of these things, and there I realized that if I invite him and if he is kind enough to talk about this network science and complex systems, that would be very good for the larger audience through this webinar platform. And Jalayer was very kind to accept the invitation, and there he is today. So he is also the founder and managing instructor of Rosen College Statistics Methodology and Research Lab. Today's webinar is mainly about network analysis and how you can use them to study complex systems and stuff like that. So I'm not going to go deeper into that. I'll leave it for Jolly to talk later on. But before we go and start the webinar, there are a couple of housekeeping things, and that is for all of you who are online via Zoom, you will see that there's an icon just like here on your screen which shows raise hand. So if you have any questions, you can actually click on this raise hand and ask your question. I just want a quick show of hands, and if anybody who can hear me, if you can just quickly raise your hands by clicking that button, I would be able to see that you are already getting it. So I see quite a few hands raised up. That's great. It means that people are listening us loud and clear. Very good. Okay. Thank you, all of you. All right. So ANAHEI, I say this in the start of every webinar, but I don't know how many of you are new listeners. ANAHEI is a non-for-profit organization, and the entire motivation and the entire our entire motivation to start ANAHEI was to promote and encourage global culture. We do a lot of student and faculty success initiatives in order to globalize people and enhance different global initiatives among member institutes, which deepens the global engagement amongst the member institutes. Now, if you want some more information about ANAHEI, you can go to the website, which is anahei.org. And get any information you want. You can become a member of ANAHEI, or your institute can become a member of ANAHEI for free. And obviously, when you go on the website, you will see that there are quite a lot of things ANAHEI is doing. Some of those things are stuff like Research in 3 Minutes, which is an initiative we recently started. Details are on the website. ANAHEI is also hosting different visiting scholar programs, different partnership programs. There are 2 journals published completely open access, free of charge. One of them is about interdisciplinary business and economics advancement. The other one is related to global education and research. There are multiple conferences organized by ANAHEI. There are certain awards. And then just like today, there are also webinar and distinguished lecture series. So we invite different experts related to different topics and invite them to come and talk over this platform. So being said that, there's another webinar coming very soon, and that's April 20th. It's related to partial least square structural equation modeling and some recent advances in model assessment. Some of you may know this guy who is in the picture. Some of you may not know him. Dr. Marco is one of the most prominent scholars in partial least square structural equation modeling, and he was kind enough to talk about some of the recent advances in PLS SEM. So I would really encourage all of you to register for this webinar, and if you can, listen to it, and you'll have an opportunity to ask him any questions you may want to ask. Other than this, for any other information, including the previous webinars or upcoming webinars, their recordings, you can also go to anahei.org/webinars, and you can get all the recordings on the website. Now, being said that, before this presentation ends, if you have any questions, please ask your questions in the chat, which is on Zoom. So if you look at your Zoom panel, you will see an option of chat. You can ask your questions there. Or this is also live broadcasting on Facebook. So if any of you has a link for Facebook, or if any of you are on Facebook and listening to me, you can also ask your questions on Facebook in the comment section, and we'll get your questions after some time, once Jolly is into his webinar, like 15-20 minutes later. So that's all with me, Jolly. You can start sharing your screen, and I will leave the floor to you. All right? Thank you.
All right, so let me start sharing my screen. Okay. So, do you see my screen now?
Yes.
All right, let me start the PowerPoint as well. Okay, perfect. So, hello everyone, and good evening from Orlando. Thank you for having me, Dr. Ali, and giving me the opportunity to share my interests with the people who might be interested in the same topic. I'm so excited to be here today and tonight. So as you said, I'm going to talk about network science and a little bit about the relationship between network science and complex systems. So in order to establish the basically terminology that we need to talk about network science, I'm going to go through some basics, so please feel free to interrupt me anytime to ask for clarification questions. All right, so in today's webinar, I will start with a very short bibliography of network footprint to see what we have in hospitality and tourism. And then I will move on with the origin of graph theory and network analysis. And after that, I will try to establish a terminology, common ground for our definitions. And then we will jump to a relatively remote topic in that sense, to complexity and complex systems. And then we will talk about network models, how network science can be related to complexity, and why it's one of the most common methods we used in complexity studies. Then I will go back to the conceptual structure of network science studies in hospitality and tourism, and what is missing based on my understanding. I will talk about a little bit about future publication potential areas to work on. And I end my presentation with some resources that might be useful for the interested individuals. So with a quick search, when I was preparing for this webinar on Scopus, I found that we have, the initial search was like about 400 articles, but when I narrowed it down to only closely related articles to network science and complexity, I found that we have 175 articles related from 51 different sources, including journal, books, and book chapters that are published in the time period between 1985 to 2018. and they have received around 20 citations per article from 326 individual authors. And on average, we have about 2 authors per article in this area. If we look at the growth, we can see that we have a high growth rate of 9.25. And as you can see here, it's growing so fast. The last part is down because it's in 2018 and we only in the third month of 2018, so that should grow as well. So this is a little bit about the condition of research in network science and complexity, and there are of course scholars more knowledgeable and well experienced in this field than me to talk about it, like Dr. Rodolfo Baggio, which is one of the, I would say, gods of network science and tourism. Or we have Dr. Noel Scott and Dr. Chris Cooper, as well as Dr. Zhang, that worked in this area. If you are interested in the potential outlets for your studies and you want to do network science, most of them are tourism journals, but we have 2 hospitality journals as well. If you check this table, we have IJCHM and IGHM as potential outlets that publish network journals, network articles as well. And we have tourism management, annals of tourism research at the top of this list. That being said, let's talk about the origins and see when this started. So network science is mainly originated in the graph theory, which is for the first time invented by Leonhard Euler. Euler, as you may know, is one of the most famous mathematicians in the history. And he actually approached this problem known as 7 bridges of Königsberg, which is a very famous problem in mathematics. And for a long time, people try to solve this empirically. So basically what happens is that we have this river is going through Königsberg city. I think it's in Russia. And it's the old name for St. Petersburg, maybe, I'm not sure. So it's divide the city, like we have a area in the middle, this island, and then we have a piece of land up there, we have a piece of land down here, and then we have a piece of land here. And these are connected to each other with these 7 bridges that we have in the image. People try to walk through these bridges and pass through these pieces of lands with a simple rule that it doesn't matter where they start or where they end, but they can only pass through these bridges only one time. And for a long time, they couldn't solve this mystery until Euler approached this problem, saying that let's take this problem and instead of looking at as a geographic problem, make these pieces of lands as dots and these bridges as lines connecting these dots. So something like this. And then he tried to solve this mathematically, and actually he proved one of the earliest theorems or axioms of graph theory, that if you have a vertex that is not end vertex or the beginning vertex of your graph and has odds number of lines to it, you cannot use all those lines to enter and exit from that vertex. So basically, that's the starting point of network analysis and graph theory, basically. So in order to establish this terminology and definitions, I want to spend some time here to talk about some terms that I'm going to use a lot and define them to you. So the first thing is these black dots here that you can see. Depends on which field of study you're coming from. You may call them vertex, which is most common among mathematicians. You can call it node if you're from social science. We might call it actor. And it can be ego, and if D is ego, all the others become alter and the other way. These lines that connect these dots together, we call them edge. We can call them link or arc. Again, depends on what's your education and research background. So here what we have is a simple network of 4 vertices. We call it order of 4. And then we have, so basically I'm going to count these as 1 because they are connecting the same vertices. 1, 2, 3, 4, and 5 edges. So this is a size of 5. And this network is undirected because none of these lines have the arrowhead at the beginning or end of it. One of the ways to show this basically network is using adjacency matrix, which is a square matrix like this, you can see, that shows what is connected to what. Now you might say why, for example, A and C is shown with 1, because this is a specific case of multiple edges I consider in this example. That's it doesn't really shows the frequency of the line. So if we have more than one connection, we can simply draw one line and put the number of connections on that. But this is just a multiple edge type of problem. So that's why I showed it with 1. And as you can see, this along the diagonal line, we have zeros because none of these vertices are connected to themselves. And another property of this matrix, this adjacency matrix, is that it is mirror from the diagonal. So what we have in upper triangle, we are going to see in the lower triangle as well. So in the next network you see here, we have, unlike the first one, we have a directed network. In this one, you can see that we have arrowheads in the network, which showing from which one to which one. It's not both way. And we have one more property added to the basically vertex B, which we call it loop. And this is basically connected to this vertex is connected to itself. And in this case, if we look at the value of the basically edges here, you can see that all of them are 1. That's why I didn't put the values, and only 1 from C to E is 85. So if these are people, and these are the number of phone calls they made, all of them call each other 1 time, but C called E like 85 times. That's the value basically showing over there. That value makes this graph a weighted graph. And here is the adjacency table for this graph down here, which is not anymore mirrored around the diagonal. And also we have not all of these values on the diagonal are 0 because B is connected to itself. Now, another important concept here, before to talk about what are these vertices and edges, is degree. And degree is simply the number of these lines around the vertex. So for example, for D here, we have a degree of 3. We call it degree centrality. So this has a degree centrality of 3 because there are 3 lines around it. So if I want to show you on this adjacency matrix, A up here has a degree of 3. So if we add these up, it's add to total of 3, and it's the same as adding these in column. So it shows that A has 3 lines out of that. So we consider these doubles as 1. So it's connected to B 1 time, it's connected to the C 1 time, and then it's connected to D. So it has a degree of 3. But in this case, in adjacency matrix down here, if you look for A, if we add them up on the row, we have a total of 1. But in column, if we add them, we have a total of 2. So in this type of directed graphs, we have in degree and out degree, basically. So if you look at vertex A, there is 1 arrow coming in. That's the in degree of 1, which is the sum of this row. And then we have 2 arrows going out, which is the sum of this column, which make the out degree of 2. So totally, we have 3 lines, again, the degree of 3, but in degree of 1, out degree of 2. Now, in the network studies, we can consider these dots or vertices as people, as employees, as students, as organizations, even as city. So it depends on the study. We can give any unit of analysis to these vertices as well as edges. So if these vertices are, for example, organization, these arrows can be, I don't know, communication between these organizations, calling to each other or sending mail to each other, or giving and borrowing money, that type of financial relationship. So any type of relationship, if these are people, this can be friendship, or if this is Facebook, this can be friendship on Facebook. So anything basically coming to your mind that is a type of dyadic relationship, relational type of data. Now, the last question the last concept I want to talk about before moving to the types of study we conduct on this is that, for example, in the in degree of node E, should we say the in degree is 2 or 86? So this is a question of whether you want to consider a weighted in degree or generally weighted degree or just a degree. So there is a relationship between C and E, and that makes the total degree of E as degree 3 with 2 in degree. But if you consider the number of times that one relationship happened, that can be 86. So basically, that's the matter of whether we consider weighted degree or just simply the degree of the structure. Now, if we are studying network, we can study the structure of network, what we have here as the structure you can see, like which node is central, how many lines are coming in, how many lines are going out, or who are the people connected. Or we can study procedures or processes. So for example, if something is passing from A to C, this can be uh, 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 like illness or something like that. It can be infectious disease. It can be a contagious behavior. It can be information. It can be adopting a specific technology or anything like that. So if we're talking about that type of studies, we need to know about some other concepts as well. So consider this one. We want to leave A and reach F. So there are multiple paths to do that. One is this one shown in red. So we have a path length of 4 from A to C to D to E to F. And then we have a shorter path here from A to D with the blue, and then from D to F. Actually, this is the shortest path between A and F. So we call this path as a geodesic. So this path is the geodesic distance between A and F, which is length of 2. Couple of more definitions, and then we start talking about complexity. So these nodes that can have different types of unit of analysis, they are not required to have the same unit of analysis. So for example, in this case, we have A, B, C, and D all in capital letter. These can be, I don't know, clubs, for example, or organizations. And then these blue dots or blue vertices can be people having the membership of these organizations. Or the other way, we can have these capital letters of A, B, C, D as people. And then these are the attitudes or ideas that these people hold about something. So for example, the person A, B, and C, they share an attitude as attitude A about the subject of our study, for example. So in this case, we call this a bipartite matrix. So in bipartite or two-mode matrix, we have two types of nodes. These are different types of nodes that are not connected to each other. We can have more than two, tripartite or quadrite. So going upper, I haven't seen any in social science. We usually have bipartite in social science. But for example, protein chain in biology can be higher than that in terms of the how many type of nodes we have in the network. This is the basically adjacency matrix showing the relationship in this network. And as you can see, it's not a square anymore because we have two types of the nodes here, one on the up here on the row, on the columns, and then the others on the rows. We call this incidence matrix. It is not anymore adjacency. It's incidence matrix, but simply taking that matrix and multiplying to the transpose. And by transpose, I mean just simply taking this matrix and turn it upside down. So if we multiply it by its transpose, then we can project it to any of these. So we can have a relationship between capital A, B, C, and D, or we can have relationships between these small letter words. So it depends on which one we put in the multiplication first that will project our network onto one of these. So another concept I'm going to talk about it here is the components. As you can see in this network, in this example, this person D with his two attitudes is not connected to the rest of the network. So we call it component. In this case, we have a network with two components. One a large component, we call it giant component in the middle, and then one component here. Even if this person has no attitudes, just himself or herself sitting here, we call it a component. So any disjoint part of the network, we call it component. Two more concepts and then we will move on. So these are different types of the networks you might see. And up here, we have a star network. So if we consider these as people and these relationships as a friendship, this is very rare in real life, yeah? So people are friend with the person in middle, but none of these are friend with each other. So this has a potential to create this relationship. Usually what we see in social settings is this kind of triangle. So we have two people, your friends, that these are your friends, they know each other, they are friends with each other as well. So this type of triangle, we call it transitivity in networks or clustering. So as you can see, this is a perfect clustering. Everybody here knows each other. This have some clustering, this have a perfect clustering, and this has zero clustering because none of the people know each other, but this has the potential to build the transitivity. And finally, one more type of networks, which is very useful in complexity studies, we call it multiplex networks. And these are usually type of networks that we use different layers. So this is let's assume that these in this example, we have 3 layers of city infrastructure. So this can be I don't know, a sewage system, irrigation system, then we can have a power system, then we might have a transportation system. So whatever systems we have, these are going to have impact on each other. So we can study them as separate layers that are interacting with each other. This is again very useful approach to network science because in complex system, we need you to use this type of multiplex networks. All right, so I'm done with the terminology section. So I assume we can move to complexity and complex systems if we don't have any questions so far.
There are no questions so far. I'll check on Facebook as well, and if there are questions, I'll stop you, Jolly, so you can continue.
Okay, all right, perfect. Complexity and complex systems. So first of all, a complex system is a system. So we have a bunch of entities that working with each other and creating a whole. That whole is more than sum of the all entities. So this is the first thing to know about complex systems. The second thing, the components we have in complex systems are usually large number of components compared to regular systems. So there are a lot of, for example, people. Those vertices can be components. And they are usually interactive and they are interacting with each other in high level of interactions. Why we call it complex? Because it's very difficult to predict the behavior and model the behavior. And that's because we have a non-linearity type of behavior with the system. The system is spontaneous, so it can clearly create order and disappear, and again become a system in later time. It's very adaptive, so it adjusts itself to others and environment. So it's continuously changing, so it's so difficult to predict its behavior. And finally, it has feedback loops that basically it learns from the environment. That's why it can adapt itself. These are some of the examples of complex systems we have. Your brain is a complex system, or any animal brain. The body we have is a complex system. The ecosystems are a complex system. The communication system we have a complex. A city is a complex system. The economy is a complex system. Human society is complex. Climate is a complex system. So when we talk about the complexity level in systems, one is those simple systems that we can study them by simply using regular techniques that we know, the statistical techniques that we are familiar with. Those techniques are also sufficient for complicated systems, because complicated systems are understandable and we can predict them. They are complicated, but still we can build a model with acceptable parsimony to predict and explain these systems. The problem starts with complex systems. In complex systems, we cannot usually use the traditional, the classic statistics we have to model the system and predict or explain the system. And the highest level is the chaos, which literally there is no pattern to predict. It's very difficult to understand, and we may never fully understand the system. Now, when we see these characteristics, this is the reason actually why network science is very popular studying complex systems, because unlike the other statistical techniques, network science is not a reductionistic technique. We are studying all the components, and they are simultaneously interacting with each other. They are connected to each other, and they have impact on each other. That's why network science is very popular in complex system studies, and we can use networks to study these systems. In order to study complex systems, we have different models in network. I'm going to talk about 5 of the most famous models. So these first 3 models I'm going to explain first, and then compare them, and then spend a little bit time at the end of my presentation on these 2 ERGM and dynamic models. So starting from the random models, trainee in 1950 started these type of models. This is what you see in a random graph. The size of those vertices is based on the degree of the node. So these larger ones have higher degree, and you can see these very small ones have degree of 1 on the periphery area. And also we have a bunch of nodes up here that are not connected to the network. So in this specific network that I simulated using trainee model, we have order of 400, meaning that we have 400 vertices that are connected to each other with 747 edges. So this is a very basically low density network. Out of all the possible lines, we only have 700 of them. And the transitivity also low. You can see that it's 0.007, meaning that in this network, at least, your friend's friend is not your friend. So in other words, clustering is not that high. The average distance to reach any nodes on this network is 4.6. As I said, the density is very low, and the mean degree is 3.73. So we have 11 components, 1 giant component in the middle, and then 10 nodes staying out of the network. And on this side, we have the degree distribution of this network. As you can see, it follows a Poisson degree distribution close to normal, with a little bit of skewness on the left, basically right skewed, sorry. So this is the random model. the problem with this model that is not very common today is not that we don't have any random, but they are not very common models, that in real world, people, organizations, cities, or anything you want to consider as a node are not connected to each other randomly. They follow a specific logic. So in 2000, basically around 2000, late 90s, physicists start studying social networks as well as other types of networks. And they realize that we have a type of network, we call it ScaleFree network. The difference here is that some of the vertices here, as you can see, are much bigger. So they have higher in degree or out degree or degree in general. So basically everyone else in this type of networks are connected to these big nodes. So that's the difference between random networks and scale-free networks that we have. In this example, again, we have 400 nodes. This time, even lower number of edges, 399. Transitivity is 0, so there is no other alternative way of connecting these nodes except from the hubs. We call these big nodes as hub, by the way. The density of the network is even lower, and the mean degree is 1.7. The average distance is much higher than the previous one. And as you can see, it's because of the type of relationships. They are all should go through these hubs. And finally, we have one component that all the nodes are connected. On this right side, you can see the distribution of the degree in this network, which is nothing close to what we had in a random network. In this one, we call these family of fat tail distributions. And this is specific distribution, we call it power law distribution, meaning that a lot of nodes with low degree, like 1, in this case, like about 300 nodes with 1 degree. These are all these small nodes. And then like a couple of them, 1 or 2 of them with 15 or more degrees, which are these larger nodes. When I compare random and scale-free networks, I'm going to show a better model to understand this. The third types of the models that solved another problem, which was the transitivity problem, we call them small world models, are based on the small world experience that most of you might be familiar. We call it 6 degree of separation. So it says basically between you and any person on this earth, on average, we have 6 other people to reach. So if you randomly send the package to somewhere and ask the person to send it to someone after 6 steps, because they are going to send it to someone that they think might know the person, after 6 steps on average, they should be able to deliver the package to the person. So this is a roughly like explanation of what we have in a small world. And as you can see here, the transitivity is very high. We have almost half of that. So 55.55 here shows that these nodes are connected to nodes around them first, and then some random connections between long distance nodes that you can see here. Distribution in this one is also following the Poisson distribution or normal distribution that we have. Now you might say, okay, we know these 3 networks now, but how they are useful in studying complex systems, that's the topic of 3 next slides I have before talking about the last couple of models. So here again, I'm showing the distribution. As you can see on the right, we have the power law distribution, which is for scale-free networks. And you can see that these are a couple of nodes with very high degree. And then we have a lot of nodes with 1 or 2 degree on this side. And then we have a Poisson distribution on this side that is a regular normal type of distribution. Now, examples of these can be the road system for the random network in United States, or the airplane routes for the scale-free. The more networks we study nowadays, we realize that we have more of these scale-free type of networks, that we have few hubs like Chicago or Miami or New York or Los Angeles here. So basically, these are the hubs of our network, and a lot of small airports around the country that are connected to these hubs. So we know that most of the complex system shows power law type of behavior, but how having a power law behavior is going to impact the studying the system. So the first thing is to know about the generative mechanism. In power law system, we have two important generative mechanisms. One is we call it reach get richer, or preferential attachment. So basically the rule is simple. If we add a node to a network, that node is more likely to connect to a node with higher degree. So in this case, this one should be more likely to connect this one. I mean, this chooses to connect this one, but generally speaking, and this is obvious because it probability-wise, it has higher probability to go to someone that is most of the other people are connected, because it's going to refer to the person basically. Now, this might be clear in case of citation network, for example. Those who have higher citations in one area, you see that collect more citations as times goes by, or any type of actually scale-free type of networks that we have. But you might say, okay, we have situations like, for example, Yahoo and Google. Google entered to the market much later than Yahoo, but then become the main hub. And that brings to the second concept. We call it the fitness concept, also known as fit get richer. So these are some inner qualities that a node has that helps the node to create more links or increase the degree. So this node, even if added to the system, added to the network later on, going to create more degree based on those inner qualities. So the quality of the paper, for example, in citation network is one of those inner qualities that I'm talking about that's going to create a lot of degree. So we have a lot of models that I put with the references. You can find yourself to your studies, but here I want to show you a small simulation that how these networks are basically built. The first one I'm going to show you is the trainee network, which is a random network, random graph based on the random graph properties. So we are going to introduce 400 nodes to the system and then randomly connect them to each other. All right, so let me set this up. Okay, so we have 400 vertices here, as you can see. Up here, you're going to see the size of the giant component. Remember, the component that is connected to most of the nodes. And we expect after average degree of 1, it explodes basically, start to gather all the nodes and connect them. And then we are going to see the histogram of the degree distribution down here. So let's start. These are going to connect randomly to each other. So here you can see little by little, the network is created. The larger component is the one with red color, but we cannot call it giant component yet because we haven't still reached to the average degree of 1. After that, we will see the giant component appears and then start collecting other nodes as well. So I speed up the process a little bit to save some time, and you can see how it grows. And as you can see, the degree of distribution, it doesn't have a specific shape yet because most of them are like degree of 1 or 2. So it's getting some shape here as well. And the line here reaches to the average degree of 1. So if I make this faster, you can see that this is going to pass the line, and then the growth rate is exponential. So here we have a giant component that start to connect to all other nodes. And little by little, this distribution is shaping. So again, if I make this faster, you will see that finally this will become a Poisson distribution, like normal distribution type. And the speed is much faster. Now it's exponentially growing. We have a little bit to include all the nodes in our network. And if we continue this process enough that I'm not going to have, we are going to have a giant, basically, hairball that all the nodes are connected to all other nodes, which in that case, we have a complete graph. And it's going to have a degree distribution histogram of uniform. So everything is the same. As you can see, this now taking that normal distribution. So this is the random graph, and it doesn't necessarily shows that preferential attachment or fitness. Now, if I start another simulation with the ScaleFree networks, you will see the difference between these two. So in this network that I'm going to show you right now, we are going to have 400. Let me see. All right, 400 nodes. And we are going to follow the same thing, the degree distribution up here, but just to start with, I introduce 5 nodes to the system. Each time, I ask the system to add 1 node at a time, and it's going to have a link of 1 to one of these. Let's check it. So now here you will see that we are going to have a power law type of distribution in a little bit, and right now it is not. And then if you look at the nodes here, it's not that more or less all of them have the same degree. We have a lot of nodes with degree of 1, and then some of the nodes like in middle here, here, or here with very high degree connecting all others. That's basically the points that hubs start forming. Complex systems usually have this characteristics of having a hub in or multiple hubs in between. So far, we have grown this network to the number of 300 something. So we're almost there, 350 and almost 400. So I can stop it right here because we have 400 nodes, 412 actually. So as you can see here, there is no limitation. People are coming and adding to the network. Organizations are entering to the network. Papers are starting citing other papers. This is more realistic. In the random models, we don't have such a property. We have a limited number of nodes, and then we start building the edges between nodes. But here, we can add nodes to the system and also build links as well. So these are 2 examples. I'm going to show this the third example of a small world on the slide that I'm going to talk about dynamic networks. So the next property that is important to know about this system is that they show different properties in terms of attacks and percolation. So basically, in percolation, we might remove one of these vertices. We call it side percolation, or we might move one of these edges. We call it bond percolation. So one on the left, A, is a random network, and one on the B that we have is basically scale-free network. So we have 2 types of errors here. One random errors, and the other one is deliberate attacks. So if we start having random errors in this network, so look at these with reds. These are the nodes that basically fail. Let's say this is internet, and these are the modems that are failing. Look at the green nodes connected to these. Very few and uniformly distributed almost. But on the other side, look at the scale-free. These reds are connected to so many greens. Now, what we can understand from this is that if this failure is random, So there's no deliberate failure. It might be this red one or any of these greens. ScaleFree network is very robust network. It shows resilient toward failure, because if one of these greens fail, nothing basically happens. And the chance that one of these greens are going to fail is higher than one of these reds, because they are more than reds. So there's higher probability that one of these low degree nodes are going to fail. And this one, if we have a couple of random failures, the whole system will break down because they have the similar number of edges. As a result, the whole system break down. Now, on the other side, on deliberate attacks, scale-free networks are very vulnerable, because if you decided to attack these red or do a site percolation of these red dots here or red vertices, the whole network is gone just by 4 or 5 of them. On this one, since none of them have so many connections, you need to attack to more of those. So basically, with almost 60% of nodes here removed in the random failure, this will still keep the form. On this one, only 27%. On the other hand, on deliberate attack situation is the same. With only 5 to 10% attacks here, you can basically destroy the whole networks. On this one, you need more attacks in order to break down the network. So this is another property of these systems. Now, the next thing and the last thing I want to compare about these two types of networks are the controlling. So on scale-free networks, we can, depends on what type of networks we're dealing, determine that the system is controllable or not. And by controlling, I mean, if we have a system here with like 7 vertices, it's very like small network. It's going, in real world, you might have like 2 million, 20 million, 20,000 vertices. One way to control the system is to control all the nodes here, which is the difficult way, of course. Another way is using maximum matching theory to find a couple of the vertices that if you inject a signal to them, you can control the whole output of the system. This is one of the recent findings in complex system studies, that with a few nodes, you can control the whole system, but you need to figure it out whether the system is controllable or not. And in order to do so, if you check the power law distribution's probability function, this gamma is very important. Studies have shown that if we approach to the gamma of 2, we call these, by the way, these nodes that we inject the signals, we call them driving nodes, because we can drive the whole system to the desired state. When it's approached, the gamma approaches to 2, we need to almost control the whole system, 100% of the system or 80% of the system. Now, by increasing gamma to higher numbers like 3, 4, 5, then you will see that, for example, in gamma of 4, with only like 2% of the whole system, we can derive it, and we can find those 2% by using maximal matching. So basically, in real world networks, these are some of the networks that are already studied. You can find the paper, they have more than these that I'm showing here, like regulatory paper, net systems. This is the yeast, which is used in wineries to produce, to turn basically sugar to alcohol. This is a one-cell microorganism, but interestingly, it's not a controllable. It's a system that if you want to control, it has an order of 4,000, meaning that 4,000 nodes it has, and you need to control 96% of those nodes in order to control the whole system. On the other side, we have like some very big networks, like cell phone networks, which is from communication networks with like 36,000 networks, and we can control it with only 20%. Or we have a prison inmate network that we can control it with only 13% of the basically prisoners here. or a study on manufacturing with 77 manufacturers with only controlling one of those, because it's only 1.3%. You can control the whole system of manufacturing and other systems as well. So it doesn't necessarily correlate with the number of vertices. Controllability of the system depends on this gamma. Again, this is very important in studying complex system, because, for example, destination image in tourism is a complex system. And in the recent study I was doing, I realized that it is not controllable. Almost 89 or 94% of the nodes are needed to control the system. And also it was a scale-free network, so it was so vulnerable to attacks from competitors, from the people who have the same destination, from countries or destinations who have the same type of image that your destination have. You can find a lot of examples in hospitality and tourism related to that. Okay, I have two more models and then I will conclude this presentation. So the recent advancements are related to ERGM models. We have a local model here from my own study published in Annals of Tourism. So in this study, I asked people that, so these are basically networks of countries and attitudes connected to them. So I asked people, mention countries that you never visit, and mention why you never visit this. This is a study we collected data early in, I don't know, 2012 with Dr. Metin Kozak and Dr. Giacomo Del Chiappa. So this network, in this network, we have these circles as the countries. For example, here we have US, we have Canada, UK, Denmark, Italy, and other. We have Kuwait here, for example. We have Saudi Arabia somewhere here. Yeah. And then we have these diamonds that are the reasons that they never visit these countries. So, for example, we have racism, hostility, lack of interest, or we have climate reason. We have what else? Negative attitude, for example. We have antagonism, and so many other reasons. So this is the data we collected from 40 individuals, and we call it in ERGM as local network. Then what ERGM does, which is an acronym for exponential random graph models, is take this network and start building random graphs based on that by adding terms to the model. So first thing, how many countries and attitudes we have. It asks the system to produce the same network with same number of vertices, but randomly connected to each other. Then it adds some attributes of these nodes that we introduce to the system. For example, whether that attitude is a kind of racist attitude or not. If that country has a, for example, similar border for the country of these people or not. These are type of the attributes we introduce to the system, and every attribute we add to the network, that network become more similar to the local network we have. After we finish building that network, we call it the global model, which is something like this. As you can see, more or less, it has the same characteristics of this network. Obviously, it's going to have different number of edges or not the same, the same relationship, because it starts with random. And then we create a lot of these models, like 10,000 models, and each time we compare it with the local model. As a result, the errors that we accumulate during this simulation creates a distribution, so we can test hypotheses. So this advancement, this elegant solution to network analysis basically moved network analysis from solely descriptive type of analysis to inferential type of analysis. So we can now test hypotheses based on the attributes of these nodes and see if the whole shape of the network is dependent on those attributes or not. So in interest of time, I'm not going to explain more than this on ERGMs. You can contact me anytime you want and we can discuss more about ERGMs. The final model I'm going to talk about is the dynamic models, which of course, as the name says, we add the elements of time to the model. So this is the very famous SI model of susceptible infected model in the disease studies that we had in the mathematics, I don't know, about 70, 80 years ago from that time. And then we have another model, we call it susceptible infected recovered. So in the first one, basically, which is applicable to adopting technology as well, it has an S shape of accepting the technology until it reached to the 100% of the population of interest. In this one, which is not very technology related, but in disease, it has a lot of use. So those who are susceptible become infected and then they recovered or removed, basically died. So we call them SIR. So we have three different graphs of susceptible, recovery, and infected. And finally, we have SIRS models. So it's similar to the first one, but it's not going to reach to the 100% because people are going to recover and the game becomes susceptible, like the influenza in this type of disease that you might become infected more than once in your lifetime. Now, these are mathematical models. Without network, we have studied a lot of disease with networks successfully. But by introduction of the dynamic networks in around 2000, 2005, we start using these models on the networks, and basically the accuracy of the models improved significantly. So one example for this can be the small world network. I can share it with you right now, and we can simulate to see how we can study this type of basically dissemination on the networks. It can be dissemination of knowledge, technology, disease, or whatever you are studying. So I'm going to create a small network with 116 nodes. So this is the small network. Let me create it again. So this is a small network. As you can see, every node is connected to immediate nodes. So this one is connected to four of the nodes around it. And then the problem in this one is if this node wants to reach, for example, to this one, consider this as a stadium of football. It should pass all these nodes and it will take a lot of time. So we take some of those lines and rewire the system. In this case, let's rewire the system with 7%. A little bit less than that. Let's make it 5%. So we took 5% of these lines and rewired them randomly. Now, if this person wants to get here, it's much easier. With 5 steps, it can get here and then move here, and 5 more steps, and we are at the destination. So the good thing is now the length is smaller. The bad thing is if a disease starts to disseminate in this system, the infection grow up in this system, it might spread so fast and get out of the control. So let's start the process. So I give the 12% chance of becoming infected and 16% chance of getting basically recovery. And then you can see that how it start growing to the system. Since the probability of recovery is higher than probability of infection here, not everyone is going to accept, going to be basically infected. And this will continue through time. But if I increase the probability of infection, all nodes might become infected. Now, this might be a little bit remotely related to tourism, but if we check the same thing on SI models, so susceptible infection model, this one, in technology adoption, actually, it has a lot of use. So we want to see who is going to adopt the technology, from who and how long it will take for the system to become infected, basically everybody using the technology. So in this case, again, 117 nodes. Let's set up the network. And this is the network we have. And I'm going to start the process of spreading the technology a little bit faster. So you can see that everybody in a short time start using the technology. That S shape that I talked about, we can see it here. And of course, these not connected components are not going to adopt it because they are not connected to the main system. So these are the type of systems that we can study with dynamic models. So now the problem, I think, is that we usually focus, these are the areas that we focused in hospitality and tourism studies. We have studied in tourism economic, marketing, tourism market, tourism development. Then we have another cluster down here for the stakeholders, destinations, decision-making, and tourist behavior and attractions. Then we have one cluster up here. The main topic is social capital. We have conceptual frameworks, competitiveness. So these are the type of studies less used, empirical data mostly. And we have ecotourism as well. And then down here, we have the knowledge, innovation, and that's that kind of dissemination and research, or like who is citing who, or what are the influential articles, or which journal is the most influential journal in the field, and that type of studies down here. So as you can see, there are so many missing elements of complex systems that we can study. Mainly we focused on social network analysis rather than network science. But if you ask what type of studies are those studies, I can show you this graph basically here. So applied complexity like biosystems engineering, innovation and technology, this can be very common in hospitality studies. And I haven't seen any using network science. We can study public health and healthcare, which is correlating with hospitality significantly. We can have urban complexity as well, which is again related to like smart designs, smart tourism, smart hospitality systems. We can study education systems and so many others that are basically right now missing in our studies. Finally, I have some resources to share, and then if there is any question, I'm more than happy to talk about it. So these are the books that, since I reached to my 1 hour, I'm not going to talk about one by one. So basically, you can later on have a look. They are for different interests. These are some general texts, by the way, here. These are some general texts that helps interested people to study about network science. Then we have some instruction books if you are interested in using like softwares to study network, different type of network analysis. These are the books I suggest. And finally, we have resources. These are only few resources or softwares that software packages that I've used. You can find more than this. The biggest package I use on R is S.NET package with all of these packages related to that. There are very good packages on R about network analysis, like iGraph. You can simulate networks and study experimental networks type of studies. If you follow this link, you will find a lot of other interesting articles, books, and software. Payek is good for big data analysis on networks, and Gephi is good for basically visualizing the networks. So this was a brief, basically, introduction of network science and complex systems and what type of models we can use and what are the typical behaviors we are expecting from scale-free networks. But the in-depth discussions of these can lead to, I believe, numerous improvement in the hospitality and tourism knowledge production. But since I have only 1 hour for my presentation, I'm going to avoid those type of in-depth discussions. and I will be happy if there is any question to answer that.
Thank you, Julie. This certainly was interesting, though a lot of it was a little bit complicated for me. So I have to go through this video a few times in order to make me used to it. It's a lot of new terminologies and everything. But thank you so much, and I really feel that it can be very helpful for a lot of researchers and scholars. We do have a few questions, though some of the questions you have already answered,
Okay.
because there was a question said, are there any programs to conduct network analysis, which you said in your last slide?
Yeah.
And then there's another question, and that is, are there any empirical papers using big data for network analysis in tourism? So
In
do you know?
tourism,
Yeah.
I haven't seen. I have one under review, but I haven't seen from anyone else. It should be, but big data in network is relatively new subject, because as big data generally is, there are a lot of articles in actually one of the papers one of the books I introduced here. If I can find the title, it's named Burst from, okay, this one. Barabashi, the book's name is Burst. This is all about big data in network. And Barabashi is one of those influential people. He is a physicist, basically. And this is about big data in network science. But paper in tourism, I can't recall. I don't remember to have it.
Okay, so with that, thank you, Jolly. And then there are a couple of more questions, which let me go through them.
Sure.
Okay, so there's one question, and that is, what type of data is used for network analysis? Which I feel I had similar question, and that was because you talked about all these networks and everything, right? So normally, let's say where people know that you distribute a questionnaire or whatever, you get this data. And then you analyze it based on different statistics or whatever. So for this network analysis, which you just talked about, where do you get data from?
Okay, yeah. The type of data we use here, we call it relational data. That's the reason that we cannot use traditional statistical techniques, because not that, okay, in a scale-free, we don't have normal distribution. It's fat tail overlaw distribution. But as you see, we have some networks with normal distribution, but still we cannot use like ANOVA. The reason is because in traditional statistics, we have a very major assumption. We call it independence of observation. So we select people, and then, for example, we ask about their attitudes towards something, and then we use ANOVA to see if there is a difference between their attitudes. In this case, people are not independent from each other. So this is like going to someone and asking the person, tell me who are your, like, name 5 are your closest friends. And then by those names, going to those 5 people and asking about 5 of those people's friends and continue. This is a snowball sampling type of thing. And we move like that to create the whole network. Now, in network analysis, we have ego type of networks. We have sampling techniques like snowball sampling, but most of the time we study the whole population, because the whole system is the interest of the study. So we study the whole population. If we want, we can take a random sample and using ERGM type of techniques generalize to similar situations, but we need to make sure that we have the whole structure of the population, or basically the same thing as being representative. So that type of relational data can be used, but relational data are not only about people. So in a recent study in tourism management, they took attractions as these vertices in I think in Baltimore, and then number of tourists that visited one of these attractions and then visited the other attraction as the link between those two. So if 10,000 people visited attraction C and then moved to attraction D, it means that C is connected to D 10,000 times. So it's not always people. This can be any type of unit of analysis on both vertices, and edges. So it can be any type of relationship between these vertices.
Right. Thank you, Jolly. Now, okay, so you are fine if I ask you questions, right? Because there are quite a few questions that came right in.
Yeah, I mean, I'm free. I don't want to waste your time.
Okay. All right. So, all right. Then there's one question, and that is, and you can answer yes, no, because people can contact you later on.
Sure.
And that is, if social network analysis can be used for literature review papers or meta-analysis type of papers.
Yeah, we can. I mean, those most of the studies, actually not most, but there are a lot of studies that in hospitality and tourism that is studying basically who is citing who. That's that type of. It's not really
Okay.
meta-analysis, but that's knowledge structure basically.
Got it. Thank you. So, okay, the next question is, what kind of theoretical network models like dynamic static can be applied to tourism research?
All of them. The major one I think is ScaleFree models, but we can use small world models, ERGM, and dynamic models. Like, yeah, all of them, except random models that are kind of old and they are not used that much because of the logic. The rest of them are usable in hospitality and tourism contexts.
All right. Then there's a question which is there a manual book for this software, which I think you talked about it, or did you not?
Yeah, so basically in the second source, slide number 23, I'm happy to share this slide with you.
Okay.
These books are explaining step by step by using either R packages or
Mhm.
one of those softwares that we have.
Right. Thank you. Yeah. So there was another question, and that was if people can get the slides. So if you share with me, we can put it on the website,
Sure.
from where just by the recorded video, so that people can access. Okay, one other question which I would ask you, and I think after that we can finish, and that is, how should we compare two networks with same or different nodes?
In case of same nodes, if like these are like people or organizations that in two separate time period we collected data, I have seen articles that use non-parametric techniques like Wilcoxon type of things to compare their degree or other types of properties like betweenness, closeness, or any other centrality. But if you want to be safe, it's better to use, like, for example, I usually use, in this case, SNA package, and I conduct ANOVA, but this is not the classical ANOVA. So this is more of a logistic regression type of ANOVA, and it compares each edge solely to see if the same relationship exists on the second network or not, and then it will give you significance level and everything else as if they are different or similar.
All right, thank you, Jolly. Now, if anybody has questions, and that's for the participants or attendees right now, or whoever watches the video in the future, can they contact you if they have any questions or anything?
Yeah, definitely. I will be happy to share my interests with others who might be interested in.
Okay, thank you very much once again. Thank you for all your time and the effort and everything. So, and thank you for all the attendees, whoever joined in, and for all the questions. And we hope to bring more webinars like this, invite maybe Jolly in the future for some other stuff.
Yeah, sure,
Right?
definitely. Thank you for having me, and thank you for taking time being here and listening and paying attention. I might start in my own YouTube channel in a year or two, talk about networks a little bit more, but definitely I will be happy to be here as well.
Sure. Take care, everybody, and goodbye.
Thank you. Bye.